So, as a reminder, on the Canvas homepage, you have had this link to the schedule. How many of you guys like this schedule? You just copied everything over. That that is kind of my goal, actually, is for you to be able to just copy it into whatever you use. It's got sure. Yeah, and to be fair, not every assignment is on here, right? Only mid-stakes and high-stakes assignments. Homeworks aren't, but the homeworks also aren't they don't have as tight of a time frame, right? You can turn in the homeworks at any point, but the unit tests and the exams are tighter. You'll notice that I did put the time in for our midterm. Good. And as a reminder, the final is not during our regular class time. It's still in this room, 5:50 to 7:50. Yeah. Thanks for asking because it's becoming second nature for me, but I know this is your first time doing it. So 5:50, 7:50. How much later is that than normal? Yeah, totally offset by 50 minutes. Um, and that's the time. You're going to get exactly 120 minutes. So if you want to come in advance to ask questions, you should be here before 5:50. If you come in after 5:50, I will have an exam ready to hand to you, and your time will end at 7:50. So in this room, May 4th, 5:50, final exam. Very exciting. Um, unless you have accommodations to take it at the testing center, in which case, do reach out and make sure that we are on the same page about that. Let's get back to our worksheet. Anybody need one of these? On nucleophiles and bases interacting with alkyl halides. So I encouraged you guys over the weekend to think about how this table might be filled out. You'll notice on that left-hand column, we're analyzing different substrates, different alkyl halides, distinguished only by their degree of substitution for the carbon. And then along the top, we are analyzing strong bases that are poor nucleophiles, strong bases that are strong nucleophiles, etc. Did you guys look at this at all over the weekend? Did you think about how these categories line up? That was a resounding no. Well, first, let's start with the top row, methyl halides. What type of elimination can I do with a methyl carbon? Very good. There is none. A methyl carbon has no carbon connected to it, and elimination requires the formation of a pi bond. So I cannot form an alkene from a methyl carbon. Methyl carbons, regardless the substrate, perform Sn2 substitution. They cannot run elimination. But why would they not run Sn1? Remind me about the mechanism for Sn1, please. Some details about it. Good. One way that we can identify that, so one molecule breaks apart and then two molecules come together with the nucleophilic attack. In that first step, we form a carbocation. That is a requirement of Sn1. A carbocation forms. And carbocations are stable or unstable on methyl carbons. Sorry? Stable. The most stable? I mean, methyl carbons are definitely an end of the spectrum, right? So if they are one end of the spectrum, they're either the least stable or the most stable. And we did talk about it right above this, right? What did we say methyl carbons are? The least stable, because having only hydrogens connected to them means that they have very little electron density to shield that positive charge. They have just become a very strong positively charged magnet. These do not form carbocations very well, and carbocations are required for Sn1. So there is no Sn1 on methyl carbons. Checks out? Now let's move up to a primary alkyl halide. I want to make sure that I have my categories here correct. If I'm reacting with something that is a strong base and a strong nucleophile. Now, methyl carbons are terrible carbocations. Primary carbons are not great carbocations. So if they can avoid it, they will avoid primary carbocations, which means they would avoid Sn1 and they would avoid E1. When we say that our reagent is both good at being a base and good at being a nucleophile, it means that if it can donate electrons to the carbon and swap out the other group, it will. But if it struggles to bond to the carbon, then it can just go and bond to a hydrogen, act as a base, and run elimination. Well, primary carbons don't have a lot of steric strain. The groups connected at that primary carbon are two hydrogens, a leaving group, another carbon. The hydrogens don't take up a lot of space, so a nucleophile can attack quite readily, which means that we see predominantly Sn2 for things that are strong bases, strong nucleophiles. You guys remember that I am terrible at distinguishing between poor and weak? I even did that here. I called one of these strong base poor nuke, and then another thing weak base weak nuke. So what's the difference between weak and poor? Nothing. They're synonymous. All right, so if we're working with a strong base, poor nucleophile means it struggles to bond to the carbon. Primary carbons don't have a lot of steric strain, but this thing already struggles to bond. That means that we'll see a competition. This reagent might substitute because there's not a lot of steric strain. It might just run elimination because it's good at taking that hydrogen. When we have something that is bad at being a base, but good at being a nucleophile, why would it run elimination? There's very little steric strain. It's very easy to be a nucleophile here, so it runs Sn2. Our last category, bad at being a base, bad at being a nucleophile. Because of this, it takes the lowest energy route, and this typically gives us Sn2 substitution. As I move down to a secondary alkyl halide, what characteristics am I changing? I'm improving carbocation stability. So if Sn1 or E1 is going to be an option, it's going to become much more relevant here. I'm increasing the steric strain. So for things that act as nucleophiles, to have to go in and substitute the carbon now requires much more energy. They have to push against all of that extra steric strain. So something good at being a base or a nucleophile is torn here. It can experience both Sn2 and E2. It is a competition between these two reactions. Things that are bad at being a nucleophile fight against too much steric strain. So they lean into their strengths and they just do elimination. Strong base, poor nuke, E2 at a secondary carbon. Something that is good at being a nucleophile but bad at being a base, again, just leans into its strength, runs substitution. Here, we see something that does not want to substitute and does not want to eliminate. It doesn't want to do substitution or elimination. And it's now fighting against more steric strain, but better carbocation stability. So these reagents have a competition between Sn1 and E1. The last row here, tertiary alkyl halides. Sn2 does not occur. The steric strain for a nucleophile to attack a tertiary carbon while the leaving group is leaving is far too high. So nothing will run Sn2. This is quite literally the opposite of the methyl halide. Nothing will run Sn2 on this position. Only E2 for things that are good at being bases. Remember, E2 is one step. I want you to think about this as strong magnets coming together and reacting. It's the first order reactions that are weak magnets. We're waiting for something reactive. We're waiting for a carbocation before anything happens. Here, this is being driven by a strong reagent, a reagent that wants to do some chemistry. We generally never take our reagents that are bad at being bases and only good at being nucleophiles to carbons that cannot allow nucleophiles. So generally, we avoid this. But if we can't avoid it, we would see a competition between Sn1 and E1. Sn2 cannot happen on a tertiary alkyl halide. And that's all that these reagents are good at doing. All they're good at doing is Sn2. So if they can't do Sn2, then maybe a carbocation forms. And if a carbocation forms, it's anyone's game between what happens next. But generally, we avoid this. You're not going to see me give you this category. Lastly, things that do not want to act as a base and do not want to substitute, again, will wait until a carbocation forms. And once a carbocation forms, they're not good at being bases or nucleophiles, so they have competition between E1 and Sn1. There is something to add to this table. Anywhere that we see competition, here's my blue, we can try to promote a winner of that competition using temperature control. If we run a reaction that has competition, meaning sometimes the molecules fumble together and result in elimination, sometimes the molecules fumble together and result in substitution. If we have that competition, we can run low temperature to promote substitution. I'm just going to abbreviate that as Sn because sometimes it's Sn2 over E2, sometimes it's Sn1 over E1. If we run with heat, sometimes we represent heat with a triangle, delta. We promote the elimination product. But if the reaction arrow does not give low temp or heat, then we should expect some of the products will be substitution products. Some of the products will be elimination. Your resulting reaction will have multiple kinds of products in it. I thought of an analogy when I went to Disney World last year, went to the beach one day, and I saw a puddle when we came into the beach, like kind of inland on the beach. And by the time we left, that puddle was gone. But my question was, did the water evaporate or did the water sink into the sand, kind of return into the low tide through the sand? I suspect both. The loss of water in that puddle next to the beach was the result of some sinking into the sand and some evaporating into the air. That loss of water had two different sources, and the same thing happens with these reactions. Multiple factors are influencing how these chemicals react and can lead to very different products that form. We can control it. Okay, now it's practice. So let's take some of our various chemicals and run them in our practice reactions on the next page. Oh, there is one thing that I want to address because I don't think I made this very clear. I've been talking about alkyl halides. So we've been saying that uh, chlorine, bromine, or iodine could serve here. But you will also see me use OTS as a leaving group. You guys might remember that this stood for a larger organic molecule called tosylate. And you can see that the oxygen of tosylate, the O of the OTS, is actually in resonance with two other oxygens, which means that once it breaks off of a carbon chain, it can hold that negative charge on three different oxygens. So it leaves with a negative charge very easily, stabilizes that negative charge very well. Some people refer to this as a pseudo-halide. It behaves like our halides behave, but it's not a halide. So if you see it, just think of it as any other halogen. It's going to leave and be substituted by a new reagent. All right, I recognize a downfall of my worksheet here is that I've given you all of these different reactions and no reagents on them or products. That probably could have been done better. So what I'm going to ask for you guys to do is pick 3 from the top and 3 from the bottom. And then to the 3 that you've assigned, pick a reagent that will run Sn1 or E1, Sn2 or E2, and then predict what the product looks like. So I want 3 different reactions from the top, 3 different reactions from the bottom, 6 total reactions, and I want 6 different reagents that you apply in each of them. I will give you an example of what this looks like, which means you can't use my exact example in one of your 6. Does that sound okay? Let me take the 1-bromo, cis-1-bromo, 3-methyl cyclohexane. You see that on the top right. I want to choose a reactant, choose a reagent that will do Sn1 or E1. So that's really just our weak base, poor nucleophile category. And you'll remember that is chloride, water, or alcohol. I'm not going to use chloride just because we don't really see chloride used that often. So I'm going to choose an alcohol. The only alcohol that I am not allowed to choose is tert butyl alcohol, and that's because that is a big, bulky molecule, so it doesn't behave like any of the others. So I'm going to pick isopropyl alcohol, 2-propanol, which you guys know in your daily lives as rubbing alcohol. Rubbing alcohol, weak base, poor nucleophile. My reactant has a secondary alkyl halide, right? Which means that I'm going to see competition between Sn1 and E1. Sn1 starts by forming a carbocation, which is achiral. It's flat. That carbocation is secondary and is surrounded by secondary carbons, so there is no rearrangement expected. My nucleophile is the oxygen, which means the oxygen will substitute the bromine, and it can either substitute from the top or it could substitute from the bottom. Can anyone explain why the alcohol can be added on after substitution from either the top or the bottom? Why do we get a diastereomeric mixture? Because the carbons are equally substituted? Not quite. Because the intermediate is achiral. The intermediate is that achiral flat carbocation, and the nucleophile can add from underneath that flat carbocation, dashed, or the nucleophile can add from on top of that achiral carbocation and add wedged. Because the carbocation is flat in the intermediate, I get both configurations of my chiral center. But heat has not been indicated, low temp has not been indicated, which means that this Sn1 product also forms in the presence of an E1 product. So an E1 product, carbocation forms, and then a base takes a beta hydrogen. A hydrogen here would form a di-substituted alkene. A hydrogen here would form a di-substituted alkene. Those are of equal stability, which means that the base could form either one of them. So there are 2 elimination products that are likely to form. Four possible major products. I could limit it to 2 if I said low temp. What 2 would I promote at low temp? The substitution products. These 2 products could be promoted at low temperature. And if I wanted to promote my elimination products, over the reaction arrow, I would write heat. So in addition to picking a reagent that you get to put over the arrow, I recommend you all take this example down. You no longer get to use this molecule or isopropyl alcohol though. Deal? In addition to that, I'd like you to decide if you want to put heat or low temp. And then in your groups, solve the products together. Or if you really want this to be challenging, swap with other groups, pick reagents for them, and then swap back and solve based on the reagents you got. Okay, I'll be coming around to answer questions, point you in the right direction. But let's do 6 questions where you assign the reagents and you predict the products. Then we're going to look at the mechanisms a little bit more in depth. Perla, do you want A copy? Okay, sounds good. Tanner and Hamza, you're welcome to work with Tabarak and Perlo, okay? Collaborate. No, that's okay. Why you were answering why it doesn't rearrange, which is good. Yeah, I know, right? So I agree. Actually, I think well, you can see that the title here is competition. No, you're right. It definitely didn't need to. It was SN1, E1, and competition, which you will only ever see SN1 and E1 on secondary and tertiaries. But you're right, this bottom group should have had more methyls, should have had more primaries. Oh, it's just the same set of molecules.
Setting more methyls and here, but
I guess you don't even need that then. They're so easy.
So, yeah.
Chloride. Isn't it funny how that one little letter changes a lot?
So, like if we did hydroxide,
This is good. Mm-hmm. Yeah. And then maybe use this one here.
Okay, so we're working on this one right here.
Okay.
It's we can use like any
Any of these ones, right?
Yeah.
pretty much, right?
And I've taken R in my example and I modified it to be isopropyl.
Yeah.
You can take R and modify it to be anything you want. And that allows you to create a series of alcohols that you can use. Well, for instance, you could make RH, in which case you just have water. Right? So Tabarak, on your example, this oxygen is your nucleophile. It bonds to the carbon, but then you lost the methyl, right? You kept the OH, but you got rid of the O to CH3 bond. Would you agree? This oxygen bonded to this carbon, and this oxygen lost its bond to this carbon. Would you agree? I mean, because you had an O to CH3 before, but now you don't. So that bond must have broke. The option that you chose to break O to CH3 is reasonable. It's actually something I'm going to address. But an easier bond to break than O to C is O to H. Notice how in my example, when I used isopropyl alcohol, the result was not an alcohol, but an ether. The OH was lost, but the O to carbon stayed from the alcohol. And it's the same with yours. This O to C will stay, but your H will be lost. So this is good, what you've got, and it will have O. Mm-hmm. And that O will still be bonded to a methyl. Exactly. Do you notice how your functional group here is an ether? You started with an alkyl halide, reacted with an alcohol, and you're left with an ether. Alcohol is a precursor to an ether. We'll look at the mechanism to make more sense of why the hydrogen is lost. This is a strong base, strong nucleophile.
Yeah.
This is a carbonyl.
That ever happened or no?
Nope. So if we're looking for an Sn1 and E1 mechanism, we need something that is not going to rip away a hydrogen right away, something that is not going to substitute right away. Correct. Hydroxide would work great on the bottom half. What we could use up above is conjugate acid of hydroxide.
H2O.
Mm-hmm. Good. And actually this whole column, right? Yep. Those are the weak nucleophiles, weak bases that will wait for a carbocation to form before they have the energy to react.
So would this wouldn't be a double bond then?
Correct.
This would be
OH.
just OH.
Yeah, you literally swap the bond to bromine for the bond to O. And I want you to think about the stereochemistry. So we saw at the end of lecture last week that the nucleophile comes in directly opposite where the leaving group is leaving.
Yeah.
So if my leaving group was wedged, then my new group will be dashed.
Is that
Oops. That's what we call the backside attack. Yep. So we can predict the stereochemistry of the product.
So this would have
Perfect.
this right here would have 4 options as well. It would just be 3 then.
Two.
Do
Ah.
this and then also couldn't also do an elimination and make an alkene like that.
Correct. And those are your 2. What were you thinking the
Why
third
would
is?
There.
Good question. Yeah. No. I see what you mean. And that's something that I didn't tell you yet. That's why. So I'll clarify that. Hi, guys. As you're predicting your products, because I'm thinking that right now you've predominantly been assigning reagents. As you begin to predict your products, I realize I didn't give you some crucial insights on stereochemistry and regiochemistry. The reactions that have carbocation intermediates. So that is Sn1 and E1. In terms of stereochemistry, we say that these give combinations of configurations. There's got to be a better way to say that. It's just escaping me at the moment. These will invert the stereochemistry. Notice how I went from wedged to dashed, and it will retain stereochemistry, wedge to wedge. Sn1 on stereochemistry gives retention and inversion at chiral carbons. Correct. That will differ when we look at Sn2. In terms of their regiochemistry, specifically for elimination, I guess maybe I should say, honestly, the Sn1 is where the stereochemistry applies the most. E1 is where the regiochemistry applies the most. You had a follow-up to that, Annie? The E1 elimination is described as giving a Zaitsev alkene. Do you guys remember Zaitsev's rule from back in section 6? Zaitsev said the most stable alkene will form, which means the most stable alkene is whichever is most substituted and whichever has the least steric strain. So a trans alkene is more stable than a cis alkene because a trans alkene has less steric strain. But a tetrasubstituted alkene is more stable than a monosubstituted alkene because it has more carbon groups coming off of it. Zaitsev alkene, most stable, aka most substituted alkene. That all comes down to the fact that it has that carbocation intermediate. That flat planar intermediate will allow anything to happen that requires the least amount of energy. Sn2 is also has some very important stereochemistry. This only gives inversion at chiral centers. And that's because of the backside attack. You guys might remember that we've addressed the backside attack in the halogenation mechanism. Halonium ring forms. It's either wedged or it's dashed. And then the halide opens the halonium ring. And the halides add anti to each other. If the halonium ring was wedged, the new halide is dashed. That backside attack gives inversion of stereochemistry. So Sn2 is stereo selective, whereas Sn1 is stereo random. Sn2 always inverts. Sn1 always gives a mixture. E2's regiochemistry depends. So two things to look out for. If you have a big bulky base, tert butoxide, it will go for the most accessible hydrogen, the one that has the least amount of steric strain, which is the anti-Zaitsev alkene. Tert butoxide always wants the most accessible hydrogen, which means that it steals from the least substituted carbon, giving the least substituted alkene. All of the other bases, hydroxide and alkoxides, and negatively charged carbons, they prefer to give the most stable alkene. They prefer the Zaitsev, but they are stereo-specific. They require antiplanar elimination. which means the leaving group and the hydrogen that is stolen have to be opposite from each other. We can look at this in a coming example. For right now, it's not actually the most crucial for you guys determining the products that you're looking for, but antiplanar means identifying the leaving group and the beta hydrogen as being anti to each other, one wedged, one dashed. If they cannot be anti to each other, they cannot go through E2. It's actually super simple. So all others prefer Zaitsev. All of the small bases prefer Zaitsev if that Zaitsev product agrees with the stereo-specific nature. So Britton just asked a good question, which was, why doesn't the hydroxide give more than one elimination product on the example he gave? And it's because the hydroxide will prefer to give the most stable. Only tert butoxide is anti-Zaitsev. It's our only anti-Zaitsev base. Okay, why don't you guys take another few minutes? 12, do you need 12 minutes? 12 minutes to keep wrapping up these problems, ask me questions, and then I would love to take a few of them and solve them on the board. Oh, so sorry. Bad timing. You okay?
Be done.
Oh,
Yeah, but I'm immunocompromised, so I don't.
oh, I'm so sorry.
It's getting better.
Yeah.
With
Okay,
this, so I did.
this is great. No, yeah, yes.
So what would happen to this additional hydrogen? The
Will-
bromine would take it?
Good. Or bromide. Yep,
Okay.
you're exactly right. Now, secondary alkyl halide, whoops, that's gone, so you can't look at it. Secondary alkyl halide with weak base, weak nucleophile gives competition. Correct.
That's what I'm doing now. And
Good.
each one is just, they're like, not the U, and our arrows were so different,
Really?
just a little bit.
Meaning you didn't have to. Oh,
And we would show them.
I gotta talk to that professor and figure out what their idea is.
But sometimes when we're doing these, like I'm adding more arrows than me because
Yeah.
like it goes from here to here. It doesn't go from here to here.
Say that again.
Like it goes
Yeah,
from
yeah.
that.
Yeah, but it doesn't.
Professor Statler is the one who teaches Gen Chem 1 and Gen Chem 2 the most.
You learn arrows in Gen Chem?
I've only taken Gen Chem 1 and Gen Chem 2.
Oh.
Didn't.
Oh. Sure, yeah, I know Holly.
Horrible class.
Wow.
Um,
Huh.
so this one it would be like this.
That's Sn2.
So what would be-
So you've given me the substitution product that water and 2-bromobutane would go through. I'm looking for the elimination product. The elimination product will form by E1.
So I would just kick this one out,
You get the same carbocation intermediate.
and then that will create a double bond. Okay.
Yeah, I mean, I'm not sure what you were thinking, but you're exactly right.
And
Now, remember, E1 wants the most stable alkene. So what is the most stable alkene that you can make? Correct. But this is not the way that it would happen. First of all,
you can double tap it and it'll erase.
sorry.
Oh, there you go.
First of all, positive charges can't
Yeah.
move, right? Just like
Then it would
just
be
like spaces.
Ace. It's been a while. It's been a while. So then I would show your.
Just like gaps in a line can't move, right? Only people can move into those. Close. So this hydrogen on this carbon needs to be removed.
Oh, so that's the one that's gonna move.
So the base steals that hydrogen. then the bonds from C to H, those shift over to form the alkene.
Over here.
Yes, but you need to show the CH bond
Okay, so I need
because the electrons from the CH bond need to move. You need to break the CH bond, so you have to show it.
this.
Perfect. And just get rid of that guy. Perfect. Nailed it.
Thank you.
Great.
Chlorine, chloride.
Chloride.
Yeah.
Yep. So
It was almost there.
those would be the substitution products. Are you trying to run this at low temps?
Yes, sure.
Because otherwise you would get elimination products as well.
Oh, okay.
Then you used,
One here,
okay, then you want to say low temp.
SN1 and E1 for each problem.
Well, sorry, it's not up there. The table told us that at a secondary alkyl halide with a weak base, weak nucleophile, I should expect to see competition.
Okay.
There is none that actually gives you just SN1 or E1. Anytime SN1 or E1 happens, they're competing with each other. Anytime I get that beach puddle, I've got competition between sand soaking in and water soaking into the sand and evaporation of the water. So yeah, write that in on the arrow, right? Low temp. And on the arrow, don't put the carbocation.
Okay, I just.
You see how it looks like you're conveying it as a reagent? But I love sketching it. So keep it to the side because I really like to see that you know what the carbocation looks like.
Okay.
Hydroxide is what type of reagent?
Wait,
Do you remember?
no.
It is a strong base, strong nucleophile, which means that it will never run SN1 or E1, right?
Okay, you're right, you're right.
But you could use water. And if you want to show E1, water with to promote elimination, heat. Yep. Now, E1 is a Zaitsev elimination. Which of these is more stable? Sorry.
Oh. Yeah. Because I thought both of these were pretty stable. Would this one be more stable?
More substituted,
Stable.
more stable. Yep. So this won't form.
Stable. Not. It won't.
I mean, it's not like it's unstable.
Okay.
Talk about major and minor products. This would be a minor product. So if I'm looking for the major product, it's just that one.
Okay.
Good. Now try doing one with methanol as your reagent.
So with the terpene oxide, it would go here, right? Because anti-Zaitsev.
Well,
No.
you raise a good point, which is that actually the most substituted carbon would be from here. That would be Zaitsev. The least substituted carbon is here. But in order to steal this, you would need to make accumulated diene, which can be hard to do.
This one, though. Is it the same? Is that what you're saying?
Oh, no, I'm
Yeah,
so
for this
sorry.
one.
No, I was reading that
No,
totally wrong. Yes, you nailed it.
okay. And
It
would
wouldn't give this,
it would it give the wedge though?
right? Because at secondary alkyl halides, terbutoxide is too bulky to substitute. So it means if you're
It would only give.
So
It would only give this.
correct, it will only do elimination.
Because it's not.
There is no competition. There's no competition between how much energy it takes for terbutoxide to do substitution against elimination at that carbon.
So if we did,
Great table.
yeah.
Using Excel.
Friends made it.
Oh, it's the same
It's
one?
the same one.
Good.
yeah. So if we were to do with an SN2 reaction down here,
So are you with terbutoxide?
no, not with.
Okay,
terpenes,
because
that only is elimination.
I didn't give you guys any good reagents to do substitution with terbutoxide. You could, If you had methyl, if you had a primary, but I just didn't set you up for that.
So if we were to do like ethyl oxide down here,
Yeah.
then it would be E2.
Good.
So it's so it would stay like this.
No, it's stereo specific, so it gives inversion. The chlorine was dashed, so the new group
So
comes in opposite.
specific is opposite, but as when E1 it stays the same. So gives retention.
We can make it a little more exciting.
Yes.
So up here, if we were to do,
Exactly.
Like you did water,
yeah,
you got reversion, inversion, and retention.
but that's because the carbocation, because it can come from either side.
Correct.
I mean, there's no chiral.
Ethoxide won't have a carbocation.
Okay.
It will have to kick that guy out of the taxi at the same time that it gets in. So it will be on the opposite seat. Do you remember? Did you see that?
Taxi like minded of it in the moment, and then I was like, "Let it go."
So that one, as it's coming from this way, it'll kick it out going that way.
Correct.
And stay.
Stays this way. Yep. Now, what atom is it that bonds to the carbon? Good.
Would you accept that or no?
I would not, especially not with the negative charge, because the oxygen is now satisfying its bond.
And then it would go.
Sure. Yeah, and you could keep ET. You could put O, ET, or draw the line structure. Great work, guys.
This way.
Hydroxide will bond
Is that the?
and kick off Br minus, but it will keep its hydrogen.
It keeps the hydrogen.
Yep. So it becomes an alcohol. And when it does that, it does it by E2, or sorry, Sn2, which means that it's always a backside attack, and you'll only see inversion of stereochemistry. So you had a wedged leaving group, it'll be a dashed OH, and that's the only product you'd see. No, well, unless, sorry, because you've got a strong base, strong nucleophile at a secondary carbon, you could also get elimination. And to do elimination, I could either steal from a primary carbon or a secondary carbon. And hydroxide does E2. It will prefer Zaitsev. It will prefer the more substituted alkene. So it would prefer elimination along the more substituted carbon. So you can get Sn2 and E2 from this reaction. If you only want to get Sn2, what should you add with your reagent? How should you clarify the temperature? Good. And then you just put that hydroxide, low temp, and all you have to show is the Sn2 product.
I have a question.
Tell me.
Are these wrong? or right? All of them. Like
Okay,
they
so
work.
this one is an anti-Zaitsev product, which it can form. We would classify it as the minor product.
Yeah, because I was like, this would be the major product.
Yep. So I would say just expect this. Yep. I would have avoided doing tert butanol here because it is so bulky, even with a carbocation. It's not super favorable, but for the concept,
Just put like,
methanol, absolutely.
just needs to have something.
Yep. And then same thing with your chloride. I would just ignore the anti-Zaitsev product and focus on the Zaitsev product that forms. Ignore the anti-Zaitsev. Good. Those are great.
This is still what form?
Yes, to a small extent. You got it. All right, with your E2 down here. So first of all, iodide, low temp in order. Oh no, sorry. It's a
Should just.
it's a weak base.
Yeah.
Yep, good. Hydroxide if I want to do elimination, high temp.
Really?
Hydroxide is a strong base and a strong nucleophile. You,
Yes.
yeah, you have it here, strong base, strong nuke,
Also,
secondary.
purity.
Yeah, you're right. You're reading the table much better than I am. So my last critique is actually the correct one, which is this is the anti-Zaitsev product.
Really?
This would be the Zaitsev product.
But then it has multiple bonds that shouldn't be there, right? Or no, you're right. Okay.
Yeah,
Because then it's 3 and 3. Okay. Okay. So we don't want that. We want that.
correct. Good. Now, to be fair, that's an E2, and I didn't give you stereochemistry, so you don't know that it's antiplanar, but then you get to assume that it's antiplanar. Does that make sense? Good. And then with this one, yes, great work.
Okay.
Sn2 and E2. Tell me.
Okay, I think the substitution seems pretty easy.
Good.
Break this bond, you get a cation on. And then your weak base, weak nucleophile bonds
Good.
to where the product is.
Yep.
This option, this was our alcohol chose.
Yeah.
When the oxygen from him, and this pulls the hydrogen off, right? And then.
If you're going to do elimination, yep,
Yeah.
exactly right. Yep.
So then, does that go into water, CH3 or just CH3H2?
And that's a good question. We would call it a protonated alcohol, CH3 OH2 plus. And up here, you haven't quite gotten your substitution product. This oxygen has a positive charge, and it will lose its hydrogen. So your final product will be an ether. Yes. Yes, perfect.
Secondary.
Exactly. They're both Zaitsev. Exactly.
We just had to do the Sn1 and E1
Yeah.
with low heat for this one, or low temp.
Yeah.
Would that be right?
Yeah. Although to abbreviate a butyl change, you would actually put capital B, lowercase u. But you would still get inversion and retention. So you would get a wedged ether and a dashed ether. Correct. All right. How about this? I would like to demonstrate some mechanisms for you guys. We can either do the mechanisms that are on the worksheet, or I have you guys, like one representative from each group, put a reaction on the board that you did and the products that you showed, and then I'll show a mechanism for forming that product. Oh, that didn't. We're gonna look at the mechanisms for these next. So we can either do the mechanisms that I've given you on the next page, or I can have you guys give an example of a reaction that you have just made. Yeah. And I will show you the mechanism for forming the product that you did. Do the new ones or the ones on the sheet. Deal. Okay, good. You had a follow-up?
Yeah, I just wanted to check that one too.
Yeah, that's perfect.
Okay.
Exactly. Great work.
Why would it not go here then? Walk me through the rules.
Mm-hmm.
I mean, it looks bad. I get that.
So it doesn't look bad. It is a functional group, the cumulated diene. But I think it requires a lot of energy to form that cumulated diene.
It's less G. That's why it's be lower.
Correct. This is just a more likely product. Yeah, I wish I had fixed this worksheet better. I think there's some reactions I could have done better on. Okay, do you guys need a break? Take quick 5 minutes and then come back at 6:10 for mechanisms. Yep. So you guys showed this. And I really appreciated that you drew out all of those bonds. You were just missing the last step, which means you didn't actually fully show your product. Correct. Correct. Our final product is not an oxygen. Our final product is an ether. Do you remember the halohydrin, haloether addition reactions? We do like bromine with water or bromine with an alcohol. And we said if we use water, we get an alcohol. And if we use an alcohol, we get an ether. Alcohols are precursors to ethers. Water is a precursor to alcohol. So in these substitution reactions, my alcohol substitutes to form an ether. If I had water here instead, water would result in an alcohol product. You guys had drawn this structure, but that wasn't the final product. The final product requires an extra deprotonation step. It's going from the OH bond back to its rightful owner, the oxygen. The E1 mechanism. Carbocation leaves. Carbocation rearrangement when applicable. Nucleophilic attack, that's this. Oh, okay. And then you see, you're looking at this page, right, where I list out the steps of the mechanism? Ah, so we got to this part, but we didn't define what that nucleophile was, right? Yeah, if you look at the next page where the mechanism is listed out, first order substitution, that final step 2A. And remember, A steps don't always happen. Like carbocation rearrangements, not happening here. Of carbocation rearrangements. Maybe. On last week Wednesday? Boy, ask me what I ate for lunch today. Yes, sometimes deprotonation needs to happen, sometimes it doesn't need to happen. It's a lot based on its on the reagent. Sorry. Okay, I want to point out some other ones that I noticed you guys giving. So if I use hydroxide, hydroxide is a strong base, strong nucleophile. So no temperature control means that Sn2 happens. And I want you to notice that whatever your nucleophile is, if it's negatively charged, then it just becomes the neutral version of that bonded to your structure. Hydroxide, OH minus, becomes an alcohol. If I used cyanide, I just get a cyano group. If I use a sulfide, like hydrogen sulfide, I just get a thiol group. So the negatively charged nucleophiles are quite nice in that they substitute on, but they don't change their structure at all. It's those neutral nucleophiles that transform in ways you might not expect. Some of them lose their hydrogens. And then with eliminations, some of you guys were showing two different elimination products, which is good that you were considering all possible eliminations. But if a reaction like E1 is Zaitsev, the anti-Zaitsev product is considered minor and not one that we would consider forming a lot of. This is the major product, the Zaitsev elimination. And I noticed this from a few groups, but I never noticed anybody predict this as an elimination product. This is actually more likely to form as a major product or as a minor product than the anti-Zaitsev elimination, because this is still more substituted, so it's more stable, but it just forms from a different conformation. It forms while the carbon chain is rotating around itself. But still, both are minor. It is kind of a challenge to teach all of the different products that you can make in these reactions. So keep practicing them. You guys have done these on active or no? And on active, you're drawing the structures. You need to be paying attention to stereochemistry, and you'll get that practice with forming those new functional groups. Do some of my old homework assignments, predict the products from those, check on the answer keys. But you'll find that we're always primarily focusing on the major product. We're not looking for the minor products. Okay, ready for some mechanisms? First, I want you guys to look at the mechanism example for first order substitution. What's another way to say first order substitution? Sn1. What reagent do I need over my reaction arrow to solve this Sn1 mechanism? Whenever you're ready. Okay. Yes, that is exactly it. An OH with a methyl attached. Brilliant. Methanol, home. Now I'm trying to avoid E1, or I'm just focusing on Sn1. If I wanted to completely avoid E1 and I only want to isolate this Sn1 product, what else could I add over the arrow? Low temp. Low temperature allows me to promote the formation of the substitution product. Okay, is it true that my final ether doesn't have stereochemistry? It's actually both wedged and dashed. So that chiral center becomes a bit meaningless to us. So sometimes I will give you a mechanism and say, ignore stereochemistry. Just don't worry about it. Other times I will give a mechanism and I will say, show the formation of the isomer shown, right? Here I've not actually given a specific isomer. I've given the version that shows that stereochemistry is lost. So that's what we'll be drawing for. We'll be ignoring stereochemistry. Step 1 in this mechanism. Carbocation forms. Leaving group leaves. I realized I didn't draw in my leaving group, did I? Sorry. Yeah, that is confusing. Now, I like to keep all of my reagents in each step, even if they're not playing a role. Does methanol play a role in step 1? No, it does not. That's not true, but it doesn't have a role with the arrows. I form a bromide and I form my methanol. Okay, I just said that it's not true that methanol plays no role. So while you copy this down, I'm going to tell you why it does actually play a role. Carbocations aren't very stable, but they can be promoted to form by polar protic solvents. Polar protic solvents, remember, are things like water, alcohols, acetic acid, things that have polar molecular dipoles, but are also slightly acidic. So methanol here is butting up its partial negative against this carbon, and it is helping to stabilize that positive charge by having its partial negative nearby. So methanol actually is helping lower the activation barrier for the carbocation to form, but it plays no mechanistic role. Step 1A, carbocation rearrangement. Anything here? No. Why won't this rearrange? The two carbons adjacent to it have the same degree of substitution. There is no stability to be gained. There's no energetic favorability for a hydrogen to shift. So, step 2, nucleophilic attack. What is my nucleophile? Anytime. Yes, the alcohol is my nucleophile, specifically the oxygen. Oxygen donates a lone pair. How do I indicate whether oxygen is forming from the top, attacking from the top, forming a bond, or attacking from the bottom, forming a bond? Can't. I can't indicate it. There's no way that my arrow can suggest that oxygen is attacking from the top or the bottom. The only way I could prove it is by drawing it in the next step. So if you want to show one of the specific stereoisomers, this would be your time to do it. But if you're following the directions that says you may ignore stereoisomers, then you don't have to show that here. Not all of our nucleophiles require a deprotonation step, but any nucleophile that has a proton does require a deprotonation step. And what takes the proton? Not bromine, bromide. Bromide is a good base or a weak base? Bromide is a weak base. So the logistics of bromide taking the proton is hard to arrange because bromide doesn't want to take a proton. One thing that the reagents and the reaction doesn't say is that we have a 1 billion time excess of alcohol. So if I wanted to, I could show another equivalence of alcohol come in at this step. I've shown it to you the whole way through, but you could draw it just at this step. And you could show methanol being the conjugate base because there is a lot of methanol to go around, and it is technically better at being a base than bromide. In reality, if bromide did act as a base, it would just pass off the proton to a neighboring methanol. So, two things here. Because I want you to be able to do the mechanism as easily as possible, you're absolutely allowed to show bromide acting as the base. But if you want to master the logistics of the chemistry here, then you could show methanol acting as the base. And instead of HBr as a byproduct, you actually get protonated methanol and bromide. Methyloxonium bromide salt. Not yummy. Sn1 mechanism. Not my favorite. Not the worst. It's fairly simple, but it's just a little tedious. Questions you have on it? In this case, because I gave you the structure like this and said you may ignore stereochemistry, it doesn't matter. But let's say that you wanted to show one of the two possible stereoisomers, because the methoxy group can add wedged or dashed. If you wanted to show one of the two, it would become relevant here after that nucleophilic attack. Do you want to see what that would look like? Makes sense? Okay. Absolutely. Yeah, methanol is a reactant in this problem. It's actually also serving as the solvent. So this is a type of reaction that we would call solvolysis. If I wanted to do this in the lab, I would need to dissolve it all in something. What am I going to dissolve it in? Well, I'm going to add, this might be a liquid, it's probably a liquid, but I'm going to add methanol to it. Methanol's definitely a liquid, and it's a very common solvent. And if I have this in excess, I can drive my equilibrium to form more product. So I'm just going to run methanol as the solvent. To which point, there's typically about 1 billion times excess of your solvent. That was a great question. Yeah, yes, you can assume it's in excess unless the equivalence is marked. That's a good way of saying it. For a lot of stuff, it's not always assumed to be stoichiometric. When we took alkenes and we hydrogenated them again with H2 and PDC, we didn't say that H2 is in excess, but we always assume that it's in excess. Alcohols, yeah, you can generally assume alcohols are in excess. Okay, questions on the Sn1? I mean, other questions. These were good questions. Easier than halogenation or harder? Different. Okay, let's look at E1. What reagent do I need over the arrow for this next E1 mechanism? A weak base, weak nucleophile. It does not matter which one I choose. Do you guys agree with that? Because I'm not running substitution, I have no preference for what reagent is doing this here. So could I use hydroxide? No. Could I use tert butoxide? Could I use methanol again, just like our last problem? Could I use water? Okay, let's run it with water. Is there evidence in this reaction to you that this is E1 and nothing else? Sorry, is there any proof that this is not E2? Is there any proof that this must be E1? But that could still be E2, right? E2 could also form an alkene. There's a rearrangement that happens, yeah? I don't just form an alkene adjacent to where my halogen is. I form an alkene without the carbon that my halogen was on. My halogen leaves, and that carbon is not involved in the alkene. There was some structural rearrangement that occurred. Okay, step 1, carbocation forms. Easy enough. I have a bond that points to my chlorine. Sorry, I'm going to keep my water here, even though the only role it's playing right now is stabilization of that carbocation. Anytime you form a carbocation, you should look for that carbocation rearrangement. We have suspicion that a carbocation rearrangement will happen here, but why? I'm hearing more substituted. What is? Yeah, the carbon to the left of my carbocation is tertiary. My carbocation is secondary. The carbocation would be more stable if it were tertiary. So I'll highlight that tertiary hydrogen. This is a hydride shift, so that H is shifting over to the carbocation position. Now you can see why that original carbon that had the chlorine ends up as a CH2 group. Step 2, deprotonation, or in other words, beta hydrogen elimination. Are you okay with the fact that we could call that different things? I am deprotonating a carbon. I'm taking a hydrogen off of a carbon. Specifically, I'm removing that beta hydrogen in order to form the alkene. Once again, chloride, not a very good base. Water, a much better base than chloride. So it's actually more reasonable for us to use water as the base here, but if you show chloride as the base, it's completely understandable. What hydrogen are they ripping off? Is it shown? So I need to draw it in. Spot the difference. I need to have a double bond at this carbon, but there's currently a hydrogen there. So I need to get rid of that hydrogen. That's the proton that I'm deprotonating. Which one are you guys going to show? Chloride or water acting as the base? You're just going to show whatever I show. I want you to think about it intentionally. What if I died right now? What would you put? Sorry. What if something happened? What would you you wouldn't keep working on your worksheet? Water, because that's similar to what we did with our Sn1. Oh, it's the opposite. Okay. Either one. I mean, could you imagine if we had put water over the arrow and then we showed chloride as the base and water did nothing? Right? It is water that is more feasible here, but I am happy to accept the chloride. Do you guys know what I just did with that? You noticed it? drew in that lone pair because I value you recognizing that it's not nuclei that are attacking, it's electrons that are attacking. You have just made hydrochloric acid. By the way, anytime you've ever worked with hydrochloric acid, you did not work with HCl. There is not a drop of HCl in hydrochloric acid. It's all hydronium chloride. Because HCl is a strong acid, it completely dissociates. E1, fairly similar to Sn1, not too bad. Before the problems? Yeah, I agree. I'm sorry. I should have also given you that regiochemistry and stereochemistry info first. Was that too fast to erase it? You guys got it all? Okay. All right, Sn2. Based on what you have, what do I need over the reaction arrow? You want to just skip to the last part? Cyanide. Hence, the nitrile forms. I form a cyano group. I will need nitrile. I'll need cyanide as my reagent. What other functional groups are in this starting material? Anytime. If you can answer that one, you can ask it. What other functional group is in that starting material and product? Ketone. Brilliant. Your wish is granted. What's your question? Yes. Correct. So this is just an example of Sn2. Yes, remember, one of your learning objectives is to fill in the missing starting material, reagent, or product for a chemical reaction. So that exercise I just had you guys do where you picked a reagent and predicted the products, that's actually not one of your learning objectives. That was a harder challenge than what you'd have to do on a test or an exam. But here, that's something you would have to do. Based on the change that I see, what reagent will get me there, including spotting the difference between E1 and E2 based on rearrangements that would or could happen, did or could happen. So I could have run this with hydroxide and temperature control and gotten an alcohol, methoxide and temperature control and gotten an ether, sulfide, azide. Yes. Okay, Sn2 mechanism, backside attack. My nucleophile is cyanide. The carbon attacks my alpha carbon, secondary alkyl halide. My leaving group leaves. This is that analogy of the guy getting into the taxi door from one side and booting out the guy from the taxi door on the other side. Whatever side the guy left from, the new guide is opposite of that. Cyanide has come in from opposite the chlorine. I didn't show the byproduct. The byproduct here is quite boring, just chloride. Yes. There is no negative charge on the carbon. Oh, I'm sorry. Yes. I thought you were talking about this carbon. Carbon does hold the negative charge. Your question was what?
For some reason, it's always been written.
Yeah, Cn minus. Logistical error. Yeah, no, that's a great question. When you write cyanide as Cn minus, it comes across as a negatively charged nitrogen. When you see the structure, you can realize that nitrogen is in a normal bonding pattern, carbon is not. How many of you took our Gen Chem 1 lab here at Slick? You remember the Lewis structures lab? You know, there's all these polyatomic ions that we ask you to know all semester long, although we rarely check in to test on it until major assignments. And how many of those polyatomic ions did you draw during that Lewis structures lab? Like 2. Hydroxide maybe? No, not even hydroxide. Ammonium is often drawn. That's it. So I'm changing that lab coming up, and I'm going to just have them draw every polyatomic ion that they are required to know, because why would you not? How many of you knew this is what cyanide looked like? I'm sure some of you did, but you'd never seen it. Yeah. Okay. And whose fault is that? Is that your fault for not knowing what it looked like, or is that your instructor's fault for not inspiring you to know what it looked like? I blame myself. Okay, questions about Sn2? Are you going to draw me more steps than that? Ever? Maybe. Because actually, let's do this. If Britton said I didn't give enough examples with methyl groups. If I react bromomethane with methanol, there's only one thing that can happen, and that's Sn2. And alcohols are precursors to ethers, so I get dimethyl ether. So technically, yes, I have a backside attack, although there's no chirality here. So there's really nothing to show for the backside attack other than the fact that it happens all at one step. But I don't have that final product yet. So if I'm dealing with something like an alcohol on a primary carbon or a methyl carbon, I might still see Sn2 as a backside attack that just requires a deprotonation step. And that deprotonation step is not hard, but it does add to the count. So there could be additional steps to Sn2 if the nucleophile needs to be deprotonated. Well, it doesn't happen all in one step, right? If you said that I put on my socks and my shoes all in one step, you know what? I guess I could, right? Stuff my sock into my shoe and then hold my sock open while I put my foot into my sock and shoe. Yeah, nobody does that. And logistically, it's quite hard to do. This technically could happen all at the same time, but logistically would be a nightmare. This bond between O and H would need to break at the exact same instance that oxygen forms a bond and kicks off the bromine. How are you going to manage for all of those chemicals to line up exactly right for that? It's certainly pushable. You could show arrows that make it seem like it's plausible. I could tell a story about a guy who puts on his socks and his shoes at the same time, but that doesn't make it plausible. Yes, yes. Correct. Yep. If my alcohol is there, it probably needs to be deprotonated at some point. Or water. Alcohol or water will need to be deprotonated. That's exactly it. Well said. The difference between Sn1 and Sn2 is not necessarily the number of steps, but what's involved in those steps. The lack of a carbocation or the presence of a carbocation. And while quite literally the difference is the order of the reactants. First order kinetics versus second order kinetics. Dependent on one molecule, unimolecular. Dependent on two molecules, bimolecular. All right, E2, what reagent can I use for this mechanism? This is still a bimolecular reaction. The rate determining step is here. This requires less energy to happen. This requires more energy. Either way, though, it's two molecules involved in both steps, so bimolecular. Now, in order to do E2, I need something strong. Strong at being a base. Hydroxide, methoxide, ethoxide, deprotonated alcohols, deprotonated water, these are great. I can use a negatively charged carbon. It's not very common because those are aggressive bases. They are scary to work with. Could I use tert butoxide for this E2 elimination? No, because tert butoxide will not form the most substituted alkene. Tert butoxide will go for the least substituted alkene. So tert butoxide, if used here, would actually give us a structural isomer to the one that we are looking for. Tert butoxide, being big and bulky, goes for the anti-Zaitsev elimination. So I'm going to use something like hydroxide here. Now this reaction, remember, is stereospecific, which means the leaving group has to be anti to the beta hydrogen. The leaving group here is OTS. Is it anti to the leaving hydrogen? It is. That tertiary hydrogen, which is assumed right now, is dashed. If I had the structure, the stereoisomer, if that hydrogen and methyl group were swapped in space, this conformation would not react. We would need a different conformation. My base is hydroxide. Hydroxide bonds to the hydrogen. The CH bond forms an alkene, and the leaving group takes its electrons and leaves the molecule. I've just formed water as a byproduct, and I've formed tosylate as a byproduct. Why did my methyl group lose its wedge? It's trigonal planar. If you draw a wedge on that methyl group, you lose some points in your product because it's not a wedged methyl group. It has no 3D configuration anymore. It's 2D planar. It's the leaving group, so it leaves with the electrons. The carbon doesn't own the electrons, oxygen does, so oxygen takes them. I like to think of this as, well, this all happens at once. Yeah, this happens in an instant. But the molecules do need to fall together or like run into each other with enough energy and the right orientation for this all to happen. And if it helps, it's all molecular orbital based. I could show you the molecular orbitals. Kirsten? Great question. Yes, without putting heat, would you agree that we should also predict the inversion of stereochemistry product? The Sn2 backside attack. You're exactly right. So that would be if I didn't say heat, and I should have prompted you guys to say heat is needed. Good question. Substitution product would form without heat. That's the last of the mechanisms I'm going to ask you to know for the final. Sn1, Sn2, E1, and E2 with alkyl halides. They are a little less straightforward. They kind of depend on the circumstance. Will you have a carbocation rearrangement? Will you not? Will you have a second deprotonation step or will you not? With heat, yep. To form the alkene, heat is required. If you're curious to see the elimination product for tert butoxide, essentially the same, all one step. E2 is a one-step elimination. All one step. Take the least substituted hydrogen, form the alkene, and kick off the leaving group. Some students have told me that it makes sense to them to think of this as a domino effect. As the base pushes electrons in to take the hydrogen, the electron density then gets pushed forward to form an alkene, and that push continues to kick off the leaving group. Yeah, kind of like a... Okay, but that's Sn2. The guy in the taxi is Sn2. Actually, it kind of gives it.
Still feels that same way to me.
Okay, but for this, it'd be a guy rips a backpack out of a taxi cab and kicks over that guy, and then that guy kicks somebody off from the other side. So he falls down and forms an alkene. You'd need a cutout of the taxi so you could see that whole thing happening. Or maybe we need to make an analogy that's not in a taxi. All right, so we have one worksheet left. And as you guys have probably learned, these worksheets are hard to do in a day. So would you like this worksheet now so you can practice the nomenclature? And then we can just start with the nomenclature right away on Wednesday. We have a few reactions left to learn, but we're not going to need the mechanisms for them for the test. And then we're going to try and compile all of these reactions in synthesis things, synthesis problems. So how do I start with one chemical and get to another? What I would like to do on Wednesday is have you guys have at least all of your worksheets that have all of the reactions, or have you bring in your table of reactions. Has anybody worked to make a table of reactions or start on one? Yeah? My recommendation again is a column with the functional group you start with, a column with the functional group you end with. That way you can spot chemical reactions by the functional change they go through. And then in the middle, the reagents that are needed for that conversion. Right? Keep in mind, you've formed so few aldehydes, so few ketones, so few carboxylic acids, but you've reacted with a lot of alkenes. So being able to identify what functional group changes you already have the tools for. That's one thing that we're going to do in this worksheet is we're going to work on more than one step synthesis. So if I hand these out to you guys tonight, work on the nomenclature, and we can start with a review of the nomenclature and solve those quickly and spend the rest of the time on reactions. Deal? Okay, I'll hand these out. I do not know if I put this on Canvas yet, so I'll check that before I leave. But otherwise, have a good night.